Hello everyone, I'm Mike Pryor-Jones from Cardiff University, and this is a re-record of a talk that I gave at the Svalbard Glaciology Meeting in Oslo, and also at the International Glaciological Society's Nordic branch meeting, also in Oslo, at the beginning of November 2021, and a couple of people have asked me about it. So this is a re-record of the talk that I gave at those events, because they weren't recorded being in-person events. So the title of the talk is Open Source Instruments for Real-Time Wireless Field Glaciology, which I'm going to tell you about in some detail. And just before we start, I'd like to make some acknowledgements, particularly to the very many people in the glaciological community who welcomed me in over the last 3 years. My background is in electronic engineering, and it's been really great to have supported the glaciological communities I've come to understand and grow in my knowledge of this very exciting discipline. I particularly like to thank Nana Carlson, who introduced me to this job, and to Liz Bagshaw, who's been my boss for the last 3 years. And I'd also like to give a quick plug to Pride in Polar Research, which is the rather cute logo on the corner of the screen, which is a network for LGBTQ+ people working in polar research. So if you're interested, go and check them out. They're on Twitter as Pride Polar. So what I thought I'd do in this talk is start by talking about the work I've been doing for the last 3 years and introduce how I came to be involved in glaciology, and then talk about things I'm going to do in the future. So starting with Cryoegg, let's just make sure the screen actually changes. Yeah. So starting with Cryoegg, Cryoegg is an instrument designed to measure what's going on in the subglacial water channel. So what's going on underneath the glacier in the water that's flowing underneath. And the idea came originally from Professor Gemma Wadham at the University of Bristol. She got a grant for it about 10 years ago and started a kind of feasibility study. And Liz Bagshaw worked on it with her. And then when Liz moved to Cardiff, she took the idea with her. And subsequently got a grant from EPSRC, the Engineering and Physical Science Research Council in the UK, to develop it in more detail. And that grant included hiring an engineer, and the engineer that she hired was me. So what Cryoegg does is it measures the conditions under the glacier. And to begin with, we started with some relatively simple physical conditions that are relatively easy to measure: water pressure, temperature, and electrical conductivity. And water pressure tells you essentially, is the water lifting the glacier up off the bedrock, which sometimes happens in the spring in alpine type scenarios, or is the water flowing out freely, in which case it's close to atmospheric pressure. Temperature is fairly obvious. Electrical conductivity is essentially a proxy for total dissolved solids, and the meltwater, freshly melted meltwater, is almost completely pure. It's almost lab grade in many cases. And so it has a very low conductivity, but as it picks up minerals from sitting around on the bottom of the glacier, then the electrical conductivity increases. So we can see when Cryoegg is in water that's freshly melted or that's been hanging around for a long time. My role essentially was to redesign the electronics in Cryoegg from the previous version that had been designed at Bristol. Essentially because a load of components were obsolete, and it was seemed like a good idea to start again. And here's the electronics on the left-hand part of the slide. So it's got the sensors in it, it's got a little processor and a battery, and then it's got a radio transmitter. And the thing that's unusual is that it reports its data by sending it wirelessly by radio through the ice to a receiver on the surface. And you can see there's a receiver on the right there. It's a reasonably large antenna on this big green plastic frame, which is actually a children's climbing frame toy called Quadro. It comes from Germany. The Quadro company very kindly donated this to our project when we said we wanted to use it for science. It's very convenient because it's a non-metallic collapsible frame that won't disturb the radio signal. We then tested Cryoegg. We made two successful tests with Cryoegg. The first one was we went to the East Greenland Ice Core Project's borehole in Greenland. And at the time, that borehole was 2.1 kilometers deep. It's filled with a kind of sticky ester-based drill fluid. And we lowered Cryoegg down on the end of the winch and looked to see if we got a signal coming up through the ice. And we did. So you can see here on the graph, the green plot shows the The green plot shows the pressure increasing as we go down the borehole, and we can also see the temperature coming from the temperature sensors. Cryoegg is at kind of ambient temperature in the drill trench before we go in, so slightly above freezing, and then it's going into this very, very cold glacier where it's -30 inside, so it gradually cools down. So the key thing really here is that we got a signal from 1.4 kilometers, nearly 1.4 kilometers down, and at that point, one of the seals failed in Cryoegg, and the instrument stopped working. But we did prove that the radio link would work, and with a slightly better mechanical design, we think we'll be capable of getting a signal right from the bottom of the northeast Greenland ice stream and 2.5 kilometers down in the future. We also took the instrument to Switzerland, and we went to the Rhone Glacier, or Rhone Glacier, depending on your preferred pronunciation. And there we worked with Maro Verde from ETH Zurich and his team, and they had made an artificial moulin the year before, essentially by hot water drilling a hole and diverting a stream into it. And that then evolved naturally over the following year. And we lowered Cryoegg into the moulin, and you can see here on the plot in red, this is the water pressure reported by Cryoegg's pressure sensor as we lower it in, and then we're into this point where it's in about 25 meters of water in the bottom of this moulin. And at that point, I left the data logger running to set up another experiment. And what you can see on the plot is that the moulin gradually drained as we were standing there over sort of 45 minutes. Now, we had no indication on the surface that this was going on beneath our feet, but the readings from Cryoegg show this up quite nicely. The other thing I quite like about this plot is that we can see the green blobs here are the reported signal level, which you can see varying up and down as Cryoegg moves around in the flowing water in the bottom of the moulin. But as the moulin level drains, you can see that the signal level gradually rises as the water attenuation is reduced. So that's really encouraging. So I'm not going to say too much more about Cryoegg, but the thing that really inspired me from that piece of fieldwork was how convenient it is to work with a wireless instrument in the field that gives you your data in real time. Because I was there with some other colleagues doing other work, and the convenience of being able to see your results as they come in while you're still standing on the glacier, rather than having to go and get data back from a data logger later on, was what inspired me to develop the next phase of work. So having said that, I'm going to sort of start with this idea of a little bit of history. And because I gave this talk originally in Norway, the historical example I chose was the Norwegian explorer, diplomat and humanitarian Fridtjof Nansen. So here is an engraving of Nansen and his team on an expedition to Greenland. It looks quite hard work. And why are they going? Well, yeah, apart from for the glory and the fame and promotion of a new nation of Norway, that he's going for scientific purpose. He's going because he wants to take water samples, and he's going to take those samples and his notes and his observations, and he's going to take them back to Oslo and do the analysis when he gets home. And what I've found quite interesting is that in some ways the basic model of polar science is still very similar to this. It's still a very expedition-centered model. What do we do when we want data from the field? Well, we go on an expedition, we take some measurements, and we bring them home. And we've got better vehicles, but we're often making these quite low technology measurements. Here we have some glaciologists doing mass balance measurement by measuring a bamboo cane with a tape measure. It's very low tech and it works very well, it's very reliable, but science has spent a long time trying to automate the process of observation, which to make things more efficient. And so I thought I would then digress briefly into a history of some of the ways that we have automated things. So this rather lovely looking machine here on the slide is Lord Kelvin's siphon recorder from 1867, which, as far as I could tell from some fairly cursory research, is the first machine that takes in an electrical signal and makes a physical recording of it that can then be reviewed at your leisure. And this was actually intended for recording signals coming along long distance telegraph cables, like the early transatlantic telegraph cable. And it works by having a little tiny coil which is disturbed by the electrical signal and moves back and forth and directs a flow of ink, comes out of a little needle-like nozzle onto a paper tape, which is then advanced by an electric motor. So it's the forerunner of both the data logger and the inkjet printer. And you can see that there's a fairly gradual slope from the siphon recorder to this thing, which is a chart recorder. These were very popular in science up until the 1980s, really, and you could still buy them now because they're still used in some industrial applications. And these chart recorders are very similar. They take in an electrical signal and they move a pen across a piece of paper that's slowly advanced underneath. It draws a graph automatically. And you can see again that, you know, modern data loggers are essentially the same idea. You take in an electrical signal that comes from your sensor and you make a recording of it, in this case, in the data logger's internal memory or on a memory card. But we're still faced with the issue of needing to go to the site where the data logger is and collect the data from it. So on my next slide, I'm going to talk about this situation in polar science. So if we imagine that we have our instrumentation in Greenland or Antarctica or Svalbard or any other remote region without good connectivity, and we want to bring that data back to our laptop, back to our, or wherever it is we work. And the simple and most commonly used method is that we put the data on a memory card, we put the memory card on an airplane, and then we bring it home again. And that's fine until you know, you have some kind of disruption to that. Maybe your instrument is damaged, the memory card is lost, it gets knocked over by a polar bear and falls in a crevasse. Some unforeseen circumstances, like say a global pandemic, prevents you going in the field to get your data, and this kind of traditional method is rather disrupted. And we've obviously known since the 1960s really that it's possible to do this kind of thing with satellite, that we could just have the data come live by satellite back from the field to our location. But until recently, this has been really expensive. And the key thing here is that particularly if you work in the polar regions, if you work at a latitude higher than 80 degrees, and in practice higher than kind of 75 even, it's starting to get a bit dodgy. There are really only two companies for a long time that offered this service. One is Iridium, and the other is Kinase. Kinase is actually the new name for the company that previously called CLS Argos, that's operated scientific satellites since the 1970s. But both of these services have satellites in polar orbit, so their satellites cover the poles, whereas the other competitors, up until very recently, were in orbits that did not cover the poles. Now, what's changing is that we have lots of new entrants into this market, and lots of companies come in launching small, lightweight satellites, which are cheap and easy to build and launch, and which are predominantly in polar orbit. And I've just picked 4 here. These are all companies that I know and have had some dealings with. And because of these new entrants to the market, they are offering service at a much lower price, and they're offering more flexibility and different approaches to how their system works. You've got a greater choice of the service that you can offer. And of course, this new market entrants have also shaken up the incumbents. And so both Iridium and Kinase are launching new services, they're launching different tariffs, and things are getting cheaper and more flexible. So that's really encouraging. And I guess one of the take-home messages I wanted to point out is how much cheaper this is starting to get. So at the moment, if you use Iridium's short burst data service, which is quite commonly used for small instruments like weather stations, that works a bit like a text message. Your instrument sends a few hundred bytes of data through the satellite network, and you then receive it at the other end. And that costs, to be on that network, costs about 17 euros a month, and then you pay a usage fee of about 30 euro cents per 100 bytes. So that adds up quite quickly over the cost of a year, and a lot of people don't bother with it as a result. The new entrants are offering much lower airtime costs. Sometimes the modems are getting a bit cheaper as well. So Swarm in the US, for example, their launch service, and it's not clear whether this is a loss leader or not, but this is their launch service. It's $5 a month and that includes 750 of their messages, which is about 140 kilobytes per month. There's Astrocast is another company I have some pricing with. The pricing's confidential, but I can tell you that it costs, their entry-level service is about half the price of a cup of coffee in Starbucks to send 1K of data per month. So satellite is going to be really, really cheap. And that's going to change the way we're going to do polar science. And I think we should move towards a situation where having connectivity to our instruments becomes the default rather than the exception. This then led to me developing this vision for a set of instruments for studying subglacial hydrology and glacier hydrology more widely, sort of inspired by Cryoegg and the work we've done on that so far. And so I've got this very crude drawing of how a glacier works. So we have some snow at one side in the accumulation zone, which then produces some meltwater, which then flows in a stream and then goes down a moulin to a subglacial channel at the bottom. And the whole glacier is sliding down the hill to the right. And the idea is that we would love to know what's going on in each of these locations. So I'd like to have instruments that measure the conditions within the snow. I call this the smart snow stake. It's a sort of like a traditional snow stake, but with electronics built into it that will tell you the snow level and also the electrical conductivity within the snow, which tells you whether the snow is wet or dry and helps you establish the onset of the melt. And then in the streams, we're going to have two instruments, one which sits in the stream and measures the temperature and the water level and the electrical conductivity. And then the blue thing there is intended to represent an automatic salt doser that puts salty brine into the stream, either on a timer or on command. And as you measure the slug of salt passing the electrical conductivity sensor on the other instrument, you can get an estimate of the discharge of the stream, assuming that your salt mixes in properly and various other issues. But that potentially gives us a way to establish what's going on in these superglacial streams. And then we have Cryoegg, which, if you have access to a drill, a hot water drill will do. You have to make a reasonably big hole, but you could then put Cryoegg down into the subglacial channel. And the idea is that it gets away from the bottom of the borehole and goes off down the subglacial channel, reporting on what's going on. And then the final group of instruments are these sausage-shaped borehole instruments, which, because I work with German-speaking researchers, became known as Cryowurst for sausage. These are intended to give more of an insight as to what's going on in the glacier dynamics. So we have one at the bed, which is measuring the subglacial conditions, and then several more further up the glacier, and they measure temperature and borehole tilt, so you can get an idea of how the glacier is moving. And then the idea is that all of these instruments are wirelessly linked using the same wireless link technology that we have from Cryoegg. And there's a receiver on the surface for picking up the signals coming from within the glacier. And then we relay the signal onto a satellite terminal and provide our data in real time. So just to summarize that, these are the measurements that the different instruments will take. And the idea is that each of these instruments is solar powered if it's on the surface, or battery powered if it's buried within the glacier. It's intended to last for at least a year, maybe much more than that. Cryoegg is the most constrained in terms of battery power, so it probably only lasts 2 or 3 years. And the Cryoverse, I think, will do 10 years at least. And they provide these kinds of measurements. And one of the things I'd like to develop as part of this more ambitious bit of the proposal is we'd like to be able to do a positioning system so we know where Cryoegg is underneath the glacier using radio positioning. So that's this plan for this proposal. And then what I'd like to do is to then change the way that we've historically done technology development within glaciology by making these instruments open source. And a lot of people are familiar with open source from software, but it's a technique that applies just as well to hardware. We can make open the designs, the electronics design, the schematics, the PCB layouts. We can make the firmware open, we can make the mechanical design drawings available and the 3D CAD and all those kinds of things. And that has a whole range of benefits to the community, the glaciological community. And those benefits vary depending on your level of engineering skill or your level of access to engineering skill. So at the most basic level, if you don't have very much interest or skill in engineering, the benefit of working with an open source instrument is that it's no longer a sealed proprietary black box. You can see inside and you can understand how it works. So if you're getting strange anomalies in your data and you're beginning to think, okay, well, maybe that's caused by some process within the instrument, you can go and look at the electronics, you can go and look at the firmware and see what's going on within the instrument. And it also means that you can more carefully replicate the work of others, because you can make an exact like for like replica of the equipment that they used. If you have slightly more engineering skill, and I suspect that this will be quite a popular option, you have the option to take the basic design and you might buy the instrument or obtain it through collaboration, and then modify it and update it. So you might choose to just change the firmware, make it do something slightly different. Maybe you interface it to some different sensors, but you're basically keeping the core of the instrument the same. There's no need to reinvent the wheel in terms of communications and power supplies and all that kind of stuff, but you can just update the bit that's relevant to you. The sort of next level down is that if you're going to design a completely new instrument, but you again recognize that you don't need to reinvent the wheel, you can reuse the subsystems. You can just go, oh yeah, we'll take the design, we'll take the power supply design, or we'll take the communications design from this other instrument, and we can, because it's open source, we can just lift the whole design and see how it works and incorporate it into our own design. And then at the sort of final lowest level, where you have the most engineering skill, you might decide actually that you're going to do the whole thing yourself, your own way, but that you can make it compatible with the rest of the instruments in the system by ensuring that you use the same radio protocols and the same data formatting, so that you can then make it part of the family and feed your data through the same infrastructure. So I think this is going to be quite powerful in terms of bringing technology to the glaciologists, particularly the glaciologists working within universities, rather than those working in the large national research institutions, which tend to have their own engineering staff. And I hope that this will be my contribution to the glaciological community over the next few years. So having talked this up quite a lot, I'm just going to say that my plan is to try and build a community around the idea of open source instrumentation in glaciology, and I'm going to be planning for various levels of collaboration. I've had quite a lot of interest actually so far from different people, and there will be people who want to be in at the engineering level and really keen to work on developing their own instrumentation very early on, and there will be other people who will be waiting for the technology to be a little bit more mature and will want to obtain something ready-made, and both of those are totally valid, and I look forward to working with people. But the funding for this has come, I got a personal fellowship through a relatively new scheme in the UK called the UKRI Future Leaders Fellowship, which came with quite a lot of very generous funding. So I'm starting in January 2022. I've got 4 years initial funding, and then that's renewable subject to a review process for a further 3 years. I'm going to be hiring 2 postdocs during 2022 for a January 2023 start, and a PhD student from September 2023. And what I'm aiming to do is create a group which contains a mixture of engineering and glaciology, environmental science type skills. And we have funding within the project for the development of the instrumentation, and also for field work in the Alps and Greenland, potentially Svalbard and some other sites as well. Yeah, it's going to be an exciting few years. Thank you for your attention to this talk, and I hope that I'll be in touch with you before too long. Thank you very much.